Uh, can you guys hear me?
Yeah.
Okay, perfect. So, welcome to this review seminar by AMACSS, the Association of Mathematical and Computer Science Students, for the course MAT A31, Calculus 1 for Mathematical Sciences. This meeting is being recorded. It will be posted on our YouTube channel, and if you can join our Discord, you will find the link to the meeting there too. So, without further ado, I think we should start. We'll be going over the practice exam and showing you guys how to work through the problems. So, yep, over to you.
All right, so I'm gonna share my screen. Please let me know if you can see it. Yeah. Can you guys see my screen?
Yeah, we can see it.
Awesome. Good, good, good. Okay, so with question one, we want to find the natural domain of the function in integral form. So I'm looking at the function right now, and I notice that we're square rooting something, right? So anytime we do this, we need to make the inner argument always greater than equal to zero, right? Because we cannot square root a negative number. And I also see that in the denominator, we have x minus one. So that tells me right away we cannot have our denominator equal to zero, right? Because then we would have an undefined number. So that means my x cannot equal to one. So from there on, we can make the inner argument of the square root greater than equal to zero, right? And from here, it tells me that, okay, since my numerator is positive, I need to make sure my denominator stays positive. So then from there on, we notice that our x has to be greater than equal to zero. And our x, our x has to be greater than equal to one. And our x cannot equal to one. So that just says, okay, our x has to be greater than one. So in interval form, it would be from one to infinity. Okay. For B, so true or false, is our function injective. So when we think about the definition of injective, we cannot have like two distinct inputs equal the exact same output. So what I mean by this is if we consider x to equal 1 and x to equal negative 1, and I substitute those values into our function, notice how we get 1 here, and we also get that f at negative 1 is 1, the same values. So this tells me that, nope, it is not injective. So it is false. Another way to do this is if you consider the graph of f of x, right, we notice that our x cannot equal zero, and it kind of just approaches upwards to positive infinity. And if I do the horizontal line test, notice how I'm touching 2 points. And so that tells me that the line test has failed, and so it is not injective. So for B, it is false. Okay, so for C, again, we have a true or false. And they're saying limit of f of x as x approaches c equals L if and only if that whole limit equals zero. So if I say, okay, we have to prove it both ways, right? So if I put it in the forwards direction where we suppose the limit of f of x as x approaches c equals L, and I try to calculate this guy, this is where the limit laws come in handy, right? Because then we can just split this into two different limits, like limit of f of x as x approaches c, minus limit of L, yeah, as x approaches C. And since we said that limit of f of x as x approaches C equals L, then we know that, okay, yeah, it's L. And we know that limit of a constant is just the constant, right? Because our L belongs to the real numbers. So it's minus L, and that cancels out, and it gives me 0. So in the forwards direction, it is true. All right, so let's check in the backwards direction. If we said that, if we suppose limit as x approaches C of f of x minus L equals 0, right? We have to make sure that the limit of f of x as x approaches C equals L. So it's kind of similar to like the forwards direction. It's just you're working a bit backwards. So again, you could split this limit. And we're trying to find this guy. And we know that this guy equals L. And I can just move this over. So then my limit of f of x as x approaches C would just be L. So it is true in the backwards. So that means we just proved that this statement is true. Okay, let's move on to D. So if f is a function with domain R and is continuous at 0 and f of 0 equals 0, then the function g is differentiable at 0. Okay, this is a little bit of a proof again, but I'm going to suppose this entire line right here. And we're just trying to figure out whether or not g of x would be differentiable at 0. So let's consider the definition of a derivative. So for g of x, g prime of x, it would equal limit as x approaches 0 of g of x minus g of 0, x minus 0, right? And if we just try to solve this limit and make sure that limit exists, then we're like, yep, okay, that means it is differentiable at 0. So it would equal limit as x approaches 0 of, so my g of x is x, f of x. And if we solve for g of 0, notice how we will get 0 because my f of 0 equals 0. So we just get 0. So minus 0 and x minus 0, that's just x. And if we simplify the top, I mean, something minus 0 is that something. So we get x, f of x over x. We can cancel out the x and we get this. But since we know that f is continuous at 0, we can simply substitute the value of 0 as x into f of x. So it just becomes limit, oh wait, sorry. It becomes f of 0. And again, that's just 0. So that means, hey, the limit exists. So that means the statement is true because it is differentiable at 0. Is this okay? I can't see the chat. Okay, I think it's okay. All right, let's go to E. Okay, so we're finding the infimum and supremum of this set. So anytime I'm given a set, I like to imagine or like write what kind of numbers are in this set. So for n, we know that it's integers and that it has to be greater than or equal to 1. So when my n is at 1, I get 0, right? N minus 1, 1 minus 1 is 0, so it's 0. When my n is 2, I get 1 over 3. When my n is 3, I get 2 over 4. Yeah. And when my n is 4, I get 3 over 5, and so on. So right now, we can figure out the infimum very easy. So it would be 0 because as n approaches like positive infinity, it just keeps getting bigger and bigger, right? The values would just be positive, right? It'd always be greater than 0. So 0 is that minimum element in the set. So your infimum would be 0. For supremum, notice how, as n grows very large, we approach 1. Oh, that error was bad. We approach 1. So we could bound this set by 1, and our supremum would be 1. So therefore, your infimum of S would be 0, and your supremum of S would be 1. Okay. All right, so this is just writing out the formal definition of the limit. So since my limit equals some L, we would start with for all epsilon greater than 0, right? And since my x is approaching positive infinity, we would use n and not delta, where my x has to be greater than n, and it implies that f of x minus L would be less than epsilon, right? Yeah. Okay. Okay, so now we have a true or false again. And it's saying if f is a differentiable function which is increasing on an interval I, then f prime of x would be greater than 0 for all x belonging to I. Right now, I'm thinking it is true. But then I realized we didn't consider f prime of x to equal 0, because that can happen. Like somehow, even if your function is increasing on that interval, it could at some point, f prime of x could equal 0. So I'm going to show you with an example. If we take f of x to equal x cubed, right? And we know that it is differentiable and continuous on real numbers, right? Because it's a polynomial, which is good. So it's a polynomial, so it is differentiable and continuous on R. I'm going to consider I to be from 0 to 5. It could be whatever. And we also know that this function is increasing on real numbers, right? Because it's cubic. So it'll be increasing everywhere. If I take the derivative of f of x, so f prime of x, that would give me 3x squared, right? And since my x belongs to I know that this derivative, right, it would be positive for all x belonging to I. However, if you take x to equal 0, then your f prime at 0 would be 0. It's not greater than 0, right? It equals 0. So we just proved that this statement's false. Why? Because at some point, your f prime of x could equal 0 in that interval. Is this okay? Okay. For H, I, and J, it's just stating, what IVT is, the Fermat's theorem, the definition of an inflection point. So I just wrote it down. Yeah. Okay, we're going to go to 2. Okay. So for 2, we're given some function, and we want to determine the domain and range of the following function. And see if it's injective. And if it is injective, let's compute the inverse and figure out that domain and range. So first, I'm going to find the domain of f because it's the easiest thing to do. I believe. So. So notice how the function is a natural log function. So that means whatever is in the argument, we just make it greater than 0. And also note that we have a square root of x. So my x, right, it has to be greater than equal to 0. Okay. So we would have to see what x could be. We just know right now that x has to be greater or equal to 0. So if I solve for it, the square root of x has to be greater than -1, and I square both sides. I get that the absolute value of x has to be greater than 1. But since we've already established that so far, we know that x is either 0 or it's greater than 0, we can just get rid of the absolute value sign. So then it just becomes x is greater than 1. Yeah. Okay, so the domain, so we've checked. So notice how we also got that x is greater than 1. And that's really just, they coincide with each other. So we're okay. So even if x is 0, we're good. We're still good. So the domain would be x belonging to real numbers such that x is greater than equal to 0. Cool. Okay. So since we know that x is greater than equal to 0, for the range, we know that, okay, that y would either be equal to 0, like when x is 0, right? Y would be equal to 0. But as x continues to grow larger and larger, y would take on positive values. It would never be negative. So your y would be greater or equal to 0. So your range would also be where y is greater than equal to 0. Okay. I think we should also take note that f of x is continuous and is increasing on its domain, right? Since it is a natural log function. And we know that considering the graphs of natural log functions, they're always increasing. But yeah. Okay, so now we gotta see whether this function is injective. So the easiest way to do that is if you consider the graph of f of x. So if we consider the graph of f of x, it looks something like this. So my x could be 0, and it just increases. Notice how it passes the horizontal line test. Like if I draw a line anywhere, it just passes it. So that means it is injective. Yeah, so it is injective. But you could also see, like, since we know that natural log functions, like ln of x, they're also injective, right? Since ln is injective on its domain, we could also do, we know that y, if we make, instead of f of x, we replace it with y, right? We could solve for x. So it'd be e to the y. We did that. It's kind of like we changed from the ln function to like exponential form. That's what I'm doing right here. And we just solve for x. So it'd be square root of x. I'm going to square both sides. And I would get x is equal to e to the y minus 1 squared. And since we know that x is greater than or equal to 0, like usually you would put an absolute value slide when you square something of a square root. But since we know that x is greater than or equal to 0, we do not need it. So this tells me right here also that it is injective too. So your inverse function would be e to the x minus 1 squared. And the domain would still be the same. It would be where x is greater than or equal to 0. And your range, same thing. It would just be where your y is greater than or equal to 0. All right, so we got the domain, we got the range. We figured out that it is injective, and we got the inverse and their domain and range. Is question 2 good? Okay, I think it is. So I'm going to pass it on to the others to do question 3 and so on.
Right, just give me 1 second. All right, so could you guys see my screen?
Yeah.
All right, perfect. So for question 3, starting off with 3A, for these questions, we don't need any like formal proofs, just like stating some some limit rules and other just like special limits we've seen to evaluate these limits. All right, so to start with, uh, first, when we see a question like this, or the first thing I do when I see like a trigonometric function, I like to use the trig limits that we've seen in class. Uh, like for example, I know there's one of the forms sine x over x, and then there's another one which is cosine of x over x. Those are your friends in this case. Using those really helps you get rid of the the trigonometric or the function. So the first thing I like to do is then I'll divide everything by x to get it in that form. So if I divide every term by x, I am left with this. And because I'm dividing by x, but because there's a square root on the 3x term, I'll divide by here, I'll divide by the square root of x squared. And this is allowed because the square root of x squared, oh, yeah, the square root of x squared will end up giving us the absolute value of x by definition. But because we're working with values that are greater than 0, we know that this, in this case, is just equal to x itself. So that's we're allowed to do that. Simplifying this, we can get, we'll still have the sine x over x, and then just simplifying the denominator, we'll get 3 over x. This is because when you bring it inside, you'll have x squared at the bottom and x at the top. So dividing it out, you'll get 3 over x. So now looking at it, can we apply direct substitution? That's like one of the first things we always want to look at. We do know that the top term ends up evaluating to 1 because of the special trig limits that we've seen. This is a constant itself, so we don't need to worry about that. And lastly, if we do direct substitution into this, 3 over some, let's see, a 0 value or 0 positive, some small number, will end up causing it to go to some high number. So if we just say infinity in this case, that won't cause any indeterminate forms. So we know that we are allowed to do direct substitution. So going forward, we know again the numerator goes to 1, and this term in the denominator, we know that we'll end up getting something like 3 over 0 positive, which in this case ends up giving us 1 over 1 plus the square root of some very large value. All right. And so this is, again, just 1 over some very large value. And this ends up just tending to 0. So this is how you would solve question 3A. Are there any questions? All right. Moving on to 3B then. It does look like there's a lot going on, and it does look a little, I guess, like scary at first because there's so many terms. But if you break it down, if you realize what every term is, you understand that there's something that you can do to simplify your, I guess, like path to solving it. You can see that there's an x squared right there, and there's an x right there. You can also see that taking the cube root of x to the 6 also gives you x squared. We have two x squared terms and an x. So what we could do to simplify heavily is divide by x squared. So doing that, let me just quickly write all the terms because it is a pretty long question. And the bottom is the cube root of, using similar logic to the previous question, we could just bring it inside, and the x squared then becomes an x to the 6 minus e to the negative x over x to the 6. Just clean this up a little. All right, there we go. So now let me simplify down. We know that some easy simplifications we can do are just getting rid of like these, I guess, like you could say the common terms. So the first term goes to -1. Dividing x by x squared gives us just x as the denominator. And well, sure, I ran out of space here. Okay, move it down here then. And let me move this here. Okay, and we can't really simplify the third term anymore. Simplifying the denominator gives us just 8, and we can't simplify this anymore. So this is what we're really left with. So now how are we going to solve this? Let's break every term, or let's break these complicated terms up into their own limits and see if we can evaluate them separately. So we'll number this as 1, this as 2, and this as 3. Okay. So with that being said now, I'll move on to the next page here. So I'll bring, we know that we need to evaluate these 3 limits. Okay. So I'm just going to copy this over so I don't have to scroll back and forth. So this is what we were working with. This is the last step we had. So looking at the first one, can we apply the limit to this term individually? And in doing so, if we were to apply the limits on each of these terms, will we get an indeterminate value? Or indeterminate form. That's what we want to see. If it doesn't give us any indeterminate forms, then we know we can apply direct substitution and simply get the answer. If it does give us an indeterminate form, however, we need to basically see, like, we need to then reassess where to go on from there. So if you notice, we can basically rewrite this in another form. We can, this is the same thing as writing e to the x times x to the 6, which we know that both of these values tend to infinity if x approaches infinity, and we know that this tends to 0. So we know the first one doesn't really do anything for us. It just gives us a constant. That's good. Let's look at the second one. Ln x over x squared. We know that this, if we were to apply direct substitution, we get the form of infinity over infinity. So we could apply L'Hopital's rule. And using L'Hopital's rule, then we'll get 1 over x over 2x, taking the derivative of both the numerator and the denominator separately. And then just simplifying from here, we'll get 1 over 2x squared. And again, that just tends to 0 if we were to apply direct substitution. So that's good. Our first two terms are just constants. So now looking at our third term, and I believe this third term is the term that we have to do the most work with to see where to go. But luckily, if you can catch on to if you could see the little trick that you have to do, you'll realize that, okay, it's also not too much work. But again, it's just if you can notice the trick, that's one of the biggest things here. So at first, it's a little confusing because I said for trig functions, I'd like to use the trig limits that we've seen, but we have an x squared here and an x here, so we can't exactly use that. And also, x is not tending to 0 as we want it to. X is going to some large value, so it's going to infinity. So what's the next thing we can do? And with trig limits, we also know that we can use squeeze theorem. And what do we really know about sine of x squared? We know that sine of any value, regardless of what's on the inside, it's always less than equal to 1, and it's greater than equal to -1. And because we know x is some large positive value, we know that if we were to divide by x, these inequalities would also not change. Okay. Now, applying the limit of the limit that we're working with, positive infinity of on every individual term, we'll be able to basically get a value for this limit itself. Because there is no concrete way to handle it or I don't see any other way to handle it other than squeeze theorem. Going forward, we know that the limit of -1 over x and 1 over x as x approaches positive infinity will give us 0. So we know that if it's both less than equals 0 and greater than equals 0, that means this value itself has to be 0. And this is just by squeeze theorem. Okay, or maybe I should write it out. By squeeze theorem. Okay, so we know that this value then ends up giving us the value of 0 as well, or this limit gives us the value of 0. So we know that all three of our, I guess you could say, problem terms, this one, and this one, they all end up evaluating to a constant. So that's really helpful for us. If we were to come back up here, we know that we're basically just dealing with constants. If we were to apply direct substitution for every single term, we know that we're working with constants. Okay? So we'll do just that then. Applying this limit to every term, we get -1 plus 0 plus 0 over the cube root of 8 plus 0. That just boils down to -1 over the cube root of 8, which is -1 over 2. Okay. That's the second, or that's 3B. Are there any questions? All right, if not, let's move on to 3C. So the first thing I notice here, again, just applying direct substitution, you'll get the limit ends up becoming the form of 0/0. So again, the very first thing I do is use L'Hopital's rule. You can also factor the denominator and then, divide out. For me, I feel like L'Hopital's rule is just a lot more straightforward. So I just like to apply that. So going forward, taking the derivative of the numerator gives us just the value of 1. Derivative of the denominator gives us 2x minus 2. Okay, does that really lead us anywhere? Not exactly, because if we were to apply direct substitution once more, we'll get 1/0, which generally or sometimes could be a valid answer because we'll just say the limit tends to infinity. But the issue here is that we are not looking at a one-sided limit. We're looking at a two-sided limit. If this was one positive, then we would be able to just say that this limit ends up tending to positive infinity. Or well, that's a little ugly. It just ends up tending to positive infinity. However, because we are looking at a two-sided limit, we have to then see, does the limit even exist? So going forward, let's do just that, and let's see if the right and left-hand side limits actually do equate to the same thing. So taking the left-hand limit gives us 1 over some value smaller than 1 minus 2, some value that's minusculely smaller than 1. This again just gives us 2 negative minus 2, which is 0 negative, right? And as we know, this will then end up giving us some negative, or it'll give us some very small negative or very small negative term, right? So negative infinity. Let's do the same thing for the right-hand side. 1 over 2x minus 2. Again, just applying direct substitution, you'll see that we get 1 plus here, minus 2. This means that we have some value that's slightly greater than 2, and we subtract 2 off of it. This gives us some value that's close to 0, very close to 0, but it's positive. And this then ends up giving us positive infinity. So what we've seen here is that the left and right-hand side limits do not equal each other. So what we could then just finally conclude is that the limit as x approaches 1 of the original term, which was x minus 1 over x squared minus 2x plus 1, it just does not exist. What the idea here was, we broke down the original limit into a easier limit to work with, and then we just checked if its right and left hand sides were equal. And because they were not equal, we can just say the limit doesn't exist. All right, that's the question 3C. Are there any questions? If not, I'll move on to question 4. So here we have to basically find all the values of a and b such that the following function is differentiable on the whole of R. Okay, so for differentiability, the very first thing we need to know is, or the very first thing we need to check is if the function is continuous. So let's do that. Checking continuity, we know that this means if we were to take the left-hand limit, which is a function x squared minus 2x minus a. Was it minus a? Yeah, minus a. This, just applying direct substitution, we could get 1 squared minus 2 times 1 minus a, which ends up just boiling down to negative 1 minus a. Doing the same thing with the right side, 1 plus gives us negative x squared plus bx plus 2. So negative x squared plus bx plus 2. Again, applying direct substitution, you'll get negative 1 squared plus b times 1 plus 2, which then ends up giving us the value of b plus 1. So we know that we want these values to be equal. So b plus 1 should be equal to negative 1 minus a. What does this mean? Simplifying it down, we get b plus a is equal to negative 2. Or in other words, let's solve for one of them in terms of the other. A is equal to negative 2 minus b. All right. So that's all the information we can get from looking at continuity. Now let's look at differentiability. Looking at differentiability, we know, again, we have to take differentiability. Okay, yeah. So knowing we have to look at both the left and right hand derivatives to see if they're equal. Or I guess we have to basically make new equations by setting the right and left hand side derivatives equal to each other. So first, let's just solve for what they are. The derivative coming from the left is equal to, let's look at what the equation is, x squared minus 2x minus a, x squared minus 2x minus a, and this is evaluated at x equals 1 or 1 negative. Okay, this is 2x minus 2. Again, x is, we're going to evaluate at x is 1 negative. And so evaluating at this value, we can just do direct substitution, and it'll give us 2 times 1 minus 2, which is 0. Now, let's look at the right-hand side derivative. We know that it's negative x squared plus bx plus 2, I believe. Yeah. We're going to evaluate this at 1 positive. So, we have to take the derivative. So, now taking the derivative, we get negative 2x plus b. And we know we're evaluating again at 1 positive, but we can just apply direct substitution here. And in doing so, we get this, or in other words, we get b minus 2. We know that these two values here should be equal because we want the question originally asked us to find a function such that's differentiable, right? So we want their left and right hand side derivatives to be equal. What we do know is that if we were to equate them here, b minus 2 is equal to 0, which implies that b is equal to 2. And since we've solved for b, we can easily solve for a, which implies that a is equal to negative 2 minus 2, which is equal to negative 4. Okay? So now with these values, I'll underline them. We know that these are the values that we were looking for both a and b. You can go and check your answers by basically plugging in the values where we solved for a and b. So plugging in a here, we know we get negative 1 minus negative 4. And this will end up giving us positive 3. Or let me just, I guess I'll write it out. Plus 4, which will end up giving us positive 3. Similarly, if we were to sub in b is equal to 2 here, we would get 2 plus 1, which is equal to 3. So that means in this case, our left limit and right limit both equal to 3. That means the function is continuous at x equals 1. Doing the same thing down here, if we were to sub in just b is equal to 2, we know that we get 2 minus 2, which equals to 0. So we got the right-hand derivative is equal to 0, and so does the left-hand derivative. It also equals 0. That means it's also differentiable at x equals 0, or sorry, x equals 1. So we know that it's both continuous and differentiable at x equals 1. That means the values of a equals b the values of A equals -4 and B equal to 2 are what we are the values that we wanted. And so that is how you would do question 4. You can also, I'm not sure if it's necessary because I was going through the prof solutions, but I'm not sure if it's necessary. But because they are asking for the entirety of R, you might have to also specify that because this is a polynomial function, so it's continuous and differentiable on its domain, which in this case is equal to -∞ to 1. And similarly with because this is also a polynomial function, it's continuous and differentiable on its own domain, which is equal to 1 and +∞. Because we're looking for a function f of x that we want to be continuous on all of R. So we know that for this part of the domain, we're continuous, or this should be this because we don't know for differentiable at x equals 1 just yet. So we know the first polynomial is both continuous and differentiable on this domain. We know the second polynomial is also both continuous and differentiable on this domain because by definition they're polynomials. So we just have to look for continuity and differentiability at x equals 1, and we solve for those values. We solve for the A and B values that allow that to happen. And because of that, we can then finally conclude that these values allow f of x, these A and B values allow f of x to be differentiable on the entire, on all real values. So yeah, that's what's needed for question 4. And yeah, so I'll be passing it on to or I'll pass it on to whoever needs to do question 5.
Okay, so I'll be doing question 5. Let me share my screen first. Okay, so for question 5, there is a function f(x) which is equal to x cubed plus x, and it says that f is continuous and injective, and AB be a point on the graph of y equals f inverse of x. And if the tangent line to y equals f inverse x at AB also passes through the point 2, 2, then what are the possible values for the slope of this tangent? And it says, note that the point 2, 2 does not lie on the graph of y equals f inverse of x. So the first thing that you should notice, like what you should think is to try to find the inverse. So because we're dealing a lot of, like we're trying to find the tangent of the inverse, so we're going to try to like find the inverse function. And we know that the inverse exists because it's injective, so that means that there will be an inverse. And it's continuous. And this function is, yeah. So we just want to try to find the inverse, we just need to just switch the y with the x. So if right now fx equals y equals x cubed plus x, then if we want to find the inverse, we just switch them up. So inverse, just switch the x with y, switch. So we get x equals y cubed plus y. And if you try to like solve and isolate for y, it's a little bit hard. but technically we don't really need to actually find the value of f inverse. You can see like the only thing that they ask us is to find the tangent line. So what's more important is the tangent line and not the actual inverse function. So the thing that you want to do if you want to find the tangent line is to first find the gradient of the tangent line. So to find the gradient of the tangent line, you just need to take the derivative and put the value of AB, so you can get it's like the normal case where you find you just differentiate the function and put in the value of A. But in this case, because we don't have it in terms of like y equals something x, we have to do implicit differentiation. So we just differentiate this and we'll get by implicit differentiation. Then we do that, so it becomes 1 equals 3y squared. And don't forget to times by dy over dx plus dy over dx. And this one we can easily solve for dy dx. So we get dy over dx equals times 3y squared plus 1 equals 1. And the same thing as dy over dx equals 1 over 3y squared plus 1. So now we have the function of the gradient, and we want to get the actual gradient, so we just plug in the value of, so we know that we want to get the gradient at a comma b, so the gradient of the tangent will be 1 over 3b squared plus 1. Then now we know that the tangent line will be in the form of, generally it's like y minus tangent line equation. It's always like this, y minus y1 equals m times x minus x1. And so basically what we need is just a point so we get x1 and a y1, and we also need the gradient, which we already have. So the point we can just put in is AB. So if we put in the point, so if you put in the point AB, you get y minus b equals 1 over 3b squared plus 1 x minus a. And now we know that the point also goes through 2, 2. So we can put in the y and x and replace it with 2, 2. So we get an equation of, because we know it passes through 2, 2. So we can plug it in. So we get 2 minus b equals 1 over 3b squared plus 1, 2 minus a. So now we have an equation that's just in terms of a and b. And so if we want to solve this, we need to get another equation that relates a and b. So we can replace either a or b with the other variable, and it will just be in terms of one equation. And we know the equation of the inverse again is inverse equation. It just needs to hold this, x equals y cubed plus y. So we know that it passes AB at AB. So we know that since the inverse has AB, that we can just replace it with AB. So A equals B cubed plus B. So now we have A in terms of B, and we can replace in the previous equation of the one above, the A in terms of B. So we get 2, substitute A equals B cubed plus B into, just name it 1. So we get 2 minus b equals 1 over 3b squared plus 1, 2 minus b cubed plus b. Oh no, it should be minus b. So then if you just multiply everything by 3b squared plus 1. We do 2 minus b times 3b squared plus 1 equals 2 minus b cubed minus b. And if you expand this, you get 6b squared plus 2 minus 3b cubed minus b equals 2 minus b cubed minus b. Then if you simplify this, you'll get the 2 cancel out and the minus b cancel out. You'll get 6b squared minus 4b cubed equals 0. I'm sorry, minus 2b cubed. And then you can factorize a b squared, and that'll be a 6 minus 2b equals 0. And this means that b is equal to 0 or b equals 3. Since we already know the value of b, the question asks us just to find the value of what are the possible values for the slope of the tangent line. So we know that the tangent line has a gradient of 1 over 3b squared plus 1. So we just need to replace the value of b with 0. So b equals 0, then the gradient is 1 over 1 equals 1. And if b equals 3, then gradient equals 1 over 3 squared plus 1, so it's 1 over 28. So you have two possible values, so it's 1 and 1 over 28. Yeah, so that's it for this question. Does anyone have any questions? If not, I will give it to the next person to do their question.
Okay, I'm gonna share my screen again. Shoot. Can you guys see my screen?
Yeah, we could.
Oh, okay, good. I thought I was muted. Okay,
No.
so for yeah, okay, so for 6, we need to find all possible values of c, so that our function has at least one x-intercept, and our c is positive, which is good. Okay. So usually I like to consider, okay, what kind of values could x take on? I like to find the domain. So from here, notice how we have a ln function, and that means we need to make the argument greater than 0, right? So, and we also have a quadratic term, and we know that x could belong to any possible real number, right? Because it's quadratic, it's a polynomial. So the domain would be just x is greater than 0. And we can also note that f of x is continuous, right? Because we have a polynomial term, and the ln function, we know that is continuous as well. Yeah, so f of x is continuous, and since it is continuous on its domain, we know that it is differentiable on its domain. We know it is differentiable. Okay, and I'm going to calculate 2 limits. Since we know that the domain is from 0 to infinity, I'm going to calculate it from the right, like approaching 0 from the right side. And these limits will come in handy for later it'll come in handy later. So when x approaches infinity of f of x. Okay. So since we know that our function's continuous, we can simply sub this guy in. So it's going to be, it's going to be positive minus ln 0 from the right. And we know that since our constant is greater than 0, c times 0 is just 0. And for the ln function, right? If we imagine the graph of our ln function, if we approach 0 from the right side, we're going to head deep towards negative infinity. So it will be negative, right? Negative times negative infinity, and that's just infinity. Okay. And if our x is approaching infinity, right, since we know it's continuous, you could simply sub it in, and you'll get c times infinity squared. I mean, that's just infinity. And since we have, it will just equal infinity, mainly because, it'll just equal infinity. Okay, just by subbing it in and considering the graph, it would. Okay, so let's consider finding the first derivative of f. All right, so f prime of x would be, just using our derivative rules, it would just be, we would take the derivative of this guy, and it would just really be the derivative of this guy minus the derivative of this guy, and that would just be 2cx minus 1 over x, right? And we know that x is greater than 0. All right, so my f prime of x would equal 0 when 2cx minus 1 over x would equal 0, right? So I'm going to multiply both sides by x because I don't like to deal with fractions. And we can do this, right? Because my x is greater than 0. It does not equal to 0. So we're okay. So it's going to be 2cx squared minus 1 equals 0. And from there on, I could simply solve for x, right? I just move this guy over here. So 2cx squared equals 1. I divide both sides by 2c. And I'm left with x squared equals 1 over 2c. So I square root both sides. And I get that x equals the square root 1 over 2c. And again, since our x is greater than 0, we do not need to consider, we don't need to put an absolute value sign, right? Because x is greater than 0. We're good. Okay, so this is the only critical point we have found. So for now, this is our only critical point we've found. And I want to classify this guy. And the easiest way to do it is to find the second derivative. Okay. All right. So my f prime prime of x equals, so we're finding the derivative of this guy, and that's just 2c plus 1 over x squared. Yeah. And notice how, since my c is greater than 0, my x is greater than 0, right, from the domain, the second derivative would be greater than 0 for all x belonging to the domain of f. Why? Because we're adding two terms, and since this term is positive, right, we would get a positive value. And we have this square here, and x is greater than 0. So this whole term would be positive. So no matter what you're doing, your second derivative is always going to be positive, which is good. So then this tells me that my critical point, the square root of 1 over 2c, is not only a local minimum, and it is a local minimum because, right, the second derivative is greater than 0, so that it would be concave up. So it would be a local minimum. But since it's the only critical point, it would actually be the absolute minimum. An absolute, minimum. Okay. Now, so in order to have at least one x-intercept, so in order to have at least one x-intercept, we can use IVT, and it would be when, so we use IVT, and we can discover that, the minimum, right? Since we know it's the absolute minimum, we need the minimum value to be less than equal to 0. But why do we need that to be less than equal to 0? Why can't it be greater than 0? Okay, this is when all this stuff we did from the beginning comes into play. If we consider the graph of f of x, and we know that c is greater than 0, we know that it's concave up, and we know that it goes from 0 to infinity. So let's say my absolute minimum is somewhere here. We know it's concave up, and we know that as the function approaches 0 from the right side, it goes to positive infinity, right? From when we calculate the limit. And as x approaches infinity, it goes upwards. So it looks something like this. But notice how our function changes depending on what c is. So if I make my function way above the x-axis, if I make the minimum value way above the x-axis, I will never have an x-intercept. Why? Because it's going upwards. It's never falling back down to the x-axis. So that's bad. I know for sure, okay, maybe if I make the minimum value equal to 0 and it goes upwards, this is okay, right? Because we have at least one x-intercept, which is good. If I make my function, if I make the minimum value be below the x-axis, then I could have more than one x-intercept, right? And like we saw before, if I make the minimum value way above the x-axis, like somewhere here, we know it's concave up, it goes to infinity, it will never touch the x-axis. So this is bad. So that's why the minimum value, the absolute minimum at our critical point, has to be less than or equal to 0. Okay, so let's determine what that minimum value would look like. That way we can figure out all the possible values of c. So f at my critical point equals c times the square root 1 over 2c squared minus ln the square root 1 over 2c. All right, and we know that has to be less than or equal to 0. So this is just like solving. I'm gonna get c times 1 over 2c minus ln of square root 1 over 2c, right? And I could cancel out the constant c, since we know that c is greater than 0. So I get half minus, here I could, instead of doing a square root, I could just write that as like an exponent, right? To the exponent half. And by my ln rules, remember, we could just move this exponent over here. So then I get half minus half times ln of 1 over 2c. And I could factor out half. So that's 1 minus ln of 1 over 2c. And we know, again, that has to be less than or equal to 0. I need a new page. Yeah, okay. All right. So now is simply just solving for c and determining what values could c be. Okay, so I'm going to divide both sides by half. All right. And I get 1 minus ln of 1 over 2c has to be less than or equal to 0. We just solve for c. So I can move this guy over here. I get negative ln 1 over 2c. That's less than equal negative 1. I divide both sides by negative 1. And since we're dividing by a negative number, we have to flip the inequality sign, right? So ln 1 over 2c has to be greater than equal 1. And I could just convert this back to exponential form. So it would be 1 over 2c is greater than equal e to the exponent 1, which is just e. And we just solve for c. So I'm going to multiply both sides by 2c. And again, I can do this since c is greater than 0. It cancels out. So 1 is greater than equal to 2ce. We're solving for c. I'm going to divide both sides by 2e. And I get that c is less than or equal to 1 over 2e. And we know that c is greater than 0. So c can take on these values as long as they're between, well, they don't equal 0, but they could be at most 1 over 2e. So therefore, c could be between 0, but cannot equal 0. And it could be less than or equal to 1 over 2e. I think that's it. Yeah. Okay. Are there any questions? All right, I'm going to pass it on.
Okay, thank you. I'll be doing question number 7. And I want to share my screen, so let me know if you guys can see it. Yep, there we go. So question number 7 is right here. State the intermediate value theorem, and then obviously we have some fun stuff with some analysis. So the IVT is pretty simple. It's been stated multiple times already in the notes, but I'll do it again. So the IVT basically says that, give me a minute. Yep, I get business. So if you have two real numbers with one less than the other without loss of generality, and you have a function f that maps this interval to R, and we're given that f is continuous on A to B. And so the question we're asked is what the IVT is. So there exists this y in R such that, now either of these can be true, But basically your y is sandwiched between your f of a and your f of b. And both of these are obviously not true at the same time. So it's an or situation. Then what this says is that there exists a C in this interval such that f of C is equal to y. So this is essentially what the IVT says. And now with question number B, we're basically asked to show that we have this set S, which is all x's in this interval a to b such that f of x is 0. And so we consider S for all x's in this interval which have their function is 0. And we're asked to show that f has a supremum and the supremum belongs to the interval. So we first need to show that S has a supremum. And the way you show it as a supremum is by using the completeness axiom. So, sorry. So what you want to show is that by completeness axiom, what you want to show is that firstly, S is non-empty. And since we're showing a supremum, it is sufficient to show that S is bounded above. If you want to show both supremum and infimum, you can also show that it's bounded below and therefore bounded from both sides. So we first show that S is non-empty. So we first show that S is non-empty. So in the question we're given that f of A is less than 0 is less than f of B. And we know that f is continuous on AB. And so essentially, by the IVT, we can conclude that there exists a C such that f of C is 0 and C belongs to this interval, A and B. And therefore, S is non-empty. The second part is rather simple. We just asked to show that S is bounded. And so clearly S is bounded above by B. And therefore we can conclude that S has a supremum by the completeness axiom. And let's call this, say, S, small s. And now we have to show that small s belongs to the interval A to B. So the way you want to do it is going to be basically arriving at a condition such that you're able to bound this supremum, right? So all we need to show here is use the definition of the supremum. So by definition of the supremum, S is more than equal to A, and because S is an upper bound, and S is less than and equal to B because B is an upper bound and your S is the supremum or the least upper bound. I'll use LUB to call it least upper bound. And so this implies by inequality properties that S belongs to A and B. All right, so I need more space here. Let's insert a page and we're good. Okay, perfect. So now we've shown part B, and oops, that should not have happened. Hope you guys can see the screen again. Yes. Okay, perfect. And now for part C, all we need to show is that f of supremum of S is 0, that is, the supremum belongs to the set. So we need to show f of S is equal to 0. And so we'll essentially go by contradiction here. So there's two possible cases if this is not true. If f of S is not equal to 0, this implies it's either greater than 0 or less than 0, right? And so if f of S is greater than 0, if less than 0, and we know S is less than equal to B, so by the IVT, we have f of S is less than 0 is less than f of B, because we know from here f of B is positive. And obviously, S is less than equal to B. Therefore, there exists something called, let's call him delta, in the interval of S to B, such that f of delta should be 0. But if this is true, then first note delta is more than S, and delta is equal to 0, which means delta belongs to S. And therefore, this contradicts the fact that our supremum is an upper bound. Therefore, this is incorrect, and f of S has to be more than equal to 0. And now we just need to make sure that f of S is not equal more than 0. So in this case, again, we use the continuity principles. And so by continuity, there exists an epsilon more than 0, for instance, such that f of x is more than 0 for all x in S plus epsilon comma B. Or S minus epsilon to S, sorry. And this holds true because if you notice, f is continuous, and we have this, which means f is sort of an increasing function. And so it has to keep increasing throughout its proportion. So using left-hand continuity, we can conclude that this statement holds. And this further implies that there has to be some point between these two. So let's say S minus epsilon by 2 belongs to this interval, obviously, by inequality properties. And this means that S minus epsilon by 2, which is less than S, is an upper bound for your set capital S. Which would contradict the fact that S is the supremum of S. Oh, S is the least upper bound of S. Essentially, it's sort of also the invocation of the approximation theorem, if you think about it in a way. And therefore, this is also incorrect. And so all we are left is that f of S is equal to 0, as was required. So that is question number 7. If you have any doubts, I'm going to check the Zoom chat now. If you have any questions, I'm here. Else, we can move on. So yeah, if you want to take a photo, we'll post these later too. But yeah, that's basically question 7. So I will stop sharing then, and you guys can take it.
Can you guys see my screen?
Yeah.
All right, perfect. Okay, so for this question, we are asked to prove this limit using the delta epsilon definition. All right, so first thing that we always do is write what does this mean? This means that we have to prove that for every epsilon greater than 0, there exists a delta greater than zero, such that if 0 is less than x minus the target value, which in this case is just 0, so we can ignore that, which is less than delta. This implies that the actual term, oh, I wrote the term wrong, the term itself tends to the value of 1. And this is should be less than epsilon. So this is what we're trying to prove. So our very next step is that we always start with like an aside portion, and we try to work at this term and see if we can break it down, see what we can do to manipulate it. So doing that, we get rewriting it. Okay, rewriting it, there we go. Now, how do we break this down? We can have some common denominators. So we'll get minus 2 plus x over 2 minus x. Okay. This simplifies down to x over 2 minus x. Okay. By absolute value properties, we can put the absolute value bars on the numerator and denominator themselves. Okay. And we can see that now we have this term right here, right? And because we're trying to find like an upper bound for it, we can basically sub in delta over 2 minus x. But because we know the bottom is not a constant, we don't know exactly how to, or how can we really bound it. We can't just bound it with delta. So what we could do is we can choose, basically, we can choose an upper bound for delta. So what we could do is assume that delta is less than equal to, let's say, the value of 1. Okay? This then tells us that from our original equation, we know we have this. And we know that delta is less than equal to 1. So that implies that the absolute value of x is less than the value of 1. What does that really mean, though? If we just, by absolute value properties, we know that means that negative 1 is less than x, which is less than 1. Okay? And now let's try to get it in the form of this right here. Okay, 1 over the absolute value of 2 minus x. Let's try to get that form. So, first thing we're going to do is multiply by negative 1. That gives us positive 1 is less than negative x, which is less than negative 1. Now, if we add 2 to every side, we get 3 is less than 2 minus x, less than 2 minus x, which is less than positive 1. Now, taking the reciprocal, so we go 1 over 3. We flip the inequalities again. 2 minus x, and this is less than 1. Now, what we do is we say that the absolute value of 1 over 2 minus x is less than the max between the absolute value of 1 and, or not absolute value, sorry. Here we just take the regular values, 1 and 1 over 3. And we know this ends up becoming 1. So we know that this term is now bounded by 1. So this term right here is bounded by 1. So subbing that in, we get delta times 1, and that ends up just giving us delta. So here we can guess delta to be the minimum between both epsilon and 1. Why would we choose 1? We chose 1 because we assumed that delta is less than equal to 1 at all times. Okay? So moving on, I'll move on to the next page. Here we start our proof. So we let epsilon be greater than 0. This is given. We choose delta to be either the minimum of epsilon or 1. And then we suppose that x satisfies the conditions we need, which is 0 is less than the absolute value of x, which is less than delta. Then it follows that, now doing similar algebra that we had before, which is 2 over 2 minus x less than 1. This then ends up giving us, as we know, it gave us x over 2 minus x, bounding this by delta as we did before, bounding x by delta, because we know that this holds. We suppose it holds. So, but we also know that because our previous bounding that we did, and because we chose that delta is at most the value of 1, we know that we can bound this 2 minus x as we did before, which then equals delta. Okay? And in this case, we just choose the value of epsilon. We choose delta is equal to epsilon. Because if we were to choose delta is equal to the value of 1, it just becomes trivially true that the proof holds. So in this case, now we've shown that we were able to bound this value by epsilon, where epsilon is some variable, which is what we wanted to show originally. And then so, because that's what we wanted to show, that's the end of the proof here. And yeah, so if there's any questions, you can say. And if there aren't, then that's question 8 done, and I'll move on to question 9.
Okay, looks like there's no more questions. So we will be back to question number 9. I hope you guys can see my screen. And so we're given a quintic polynomial and we're asked how many real solutions does the equation have. So the essential approach to doing this problem is using a couple of theorems from the course. Always remember in the exam when you have, oops, it's happening. When you have a problem about the number of roots, always remember you have to use the one or both of the mean value theorem and the intermediate value theorem. But it's hard to find roots when they're equal to 4, right? So let's get rid of that problem first. So let's consider a polynomial which is f of x. And let's say the polynomial is x to the 5 plus x cubed plus x minus 3. And we have to find all x such that f of x is equal to 0. And the way we go ahead is a simple theorem that a lot of you might know from high school is the fundamental theorem of algebra. And essentially, the conclusion of the fundamental theorem of algebra is that the maximum number of real roots of a polynomial of degree n is n. So this polynomial has at max 5 roots, but we have to find out exactly how many roots this has. So Let's start by using the IVT first, right? So firstly, we have to note that f of x is a polynomial, and therefore it is continuous and differentiable on R by the properties of polynomials, and therefore on any subset of R. Now, if you plug and chug x equals 1, you can see that x equals 1 is a possible root for this. But let's do it by IVT. So therefore, f is continuous on both 0 and 2. And so what this essentially implies is if you look at f of 0, it's going to be minus 3. And f of 2 is going to be 2 to the 5 plus 2 to the 3 plus 2 minus 3, which is going to be 39. And clearly 0 lies between 3 and 39. And therefore there exists an x in 0, 2 such that f of x is equal to 0. So there is at least one root, which we luckily know is 1 because we guessed it. And then now we got to show that this is the only root. And the way we do it is by using the mean value, by using the derivative. So you consider f dash x, and your f dash x is going to be the derivative of f of x. So oops. And so we can use the power rule here to say it's going to be equal to this. Now you can essentially notice a couple of things here. You can first notice that 5x to the 4 is more than equal to 0 because x to the 4 is more than equal to 0, and 3x squared is more than equal to 0 because x squared is more than equal to 0, and therefore this whole thing is going to be more than equal to 1, which is more than 0. This is by the property of R and inequalities. And so, because this is always positive, this implies that f is strictly increasing. So, when you have a very graphical perception of this, it's essentially that if you have just let this be your x-axis, let this be your y-axis, and so your function is of somewhat this form, right? So it crosses the axis at x equals 1, and then it's strictly increasing. So it could be a curve too, but it's always going up. And so it will never cross the x-axis again. And so you can confidently conclude that f has exactly one root at x equals 1. Any question? No questions, I see. Okay, perfect. Fun trivia fact. There are formulas to calculate the roots of a quadratic polynomial or a cubic polynomial, but there's actually no formula to calculate the roots of a quintic polynomial like this. And the reason why is the driving motivation behind a fancy part of math called as Galois theory, which a lot of you might learn in your upper years. So a nice motivation from this problem, I would say. Yeah. Anyways, let's move on. This is the 10th question. It's a rather elegant question. So we have A and B belonging to R with A less than B, and we have a function that's differentiable on AB. We have to use the mean value theorem to show that f dash x equals 0 for all x on A and B implies that f is constant on A and B. So essentially, we have to show that if there is, so intuitively this makes a lot of sense because if your rate of change for your function is 0 and your function is not changing, it means it's constant, right? But the definition of a constant is for all x comma y in the domain of a function, x not equal to y and f of x equals to f of y implies f is constant. So your function has a constant value for all x and y in its domain, right? And so the way we can start by showing, because this is a universally quantified statement, we want to start by taking up something that's arbitrary, right? So our domain is A to B. So let x comma y belong to A and B be arbitrary elements. Note, also without loss of generality, you could say y is less than z. Since f is differentiable on AB and differentiability obviously implies continuity, you can say f is continuous on any subset of AB. So let's say the subset is YZ. And obviously, since YZ is a subset of AB, F is differentiable on YZ too. And this is really nice because this is essentially the hypothesis of the mean value theorem. And therefore, we can apply the MVD on F across YZ. And therefore, you could say that there exists a C belonging to this interval YZ of arbitrary elements such that f dash of C is equal to f of Z minus f of Y over Z minus Y. And note that C belongs to Y minus Z, which is a subset of A and B, and therefore C belongs to A and B. And we have this given that for all x in A and B, f dash x is 0, which means f dash c is 0, which means f of z minus f of y over z minus y is equal to 0. But note y is less than z. So this just implies f of z is equal to f of y. And since y and z were arbitrary, we can conclude that for all x and y in the domain of f dash, wait, oh yeah, x not equal to y, and f of x equals to f of y. Therefore, f is a constant function on A to B. Is that clear? Any questions I can answer? If not, we can move on to the last question, I think, which is question 11.
Okay, so I'll be doing the last question. So let me first share my screen. So the last question is a sketching question, and it's always guaranteed to have a question like this in your final. Just the function might be different. So, but then the steps is always the same, where they'll just tell you to do all these steps, and in the end you just draw it based on the steps. So the first question is this. The function is fx equals x plus square root of x squared minus 1. So the first question says to state the domain of f. So generally to find the domain of any function, just see where like anything that can break the function, like make it not valid, happen. So in this case, we have x, which is okay because x is valid for any value of x, but the problem lies with the square root, where square root has to be non-negative. So we know that x squared minus 1 has to be greater than or equal to 0. So this means that x squared is greater than or equal to 1, which means that x is less than or equal to minus 1, or x is greater than or equal to 1. So we know the domain is going to be, if you want to put it as a set, domain is x is a real number such that x is greater than or equal to 1, or x is less than or equal to minus 1. So this will be our domain of the function. The next thing is to do the vertical and horizontal asymptotes. So in this case, we will not have a vertical asymptote because generally for vertical asymptotes, it will be for like if you have a fraction, then you just set the denominator to 0. Generally it's that. Then, so it's just whenever it's a fraction as you equate to 0. So there's no vertical asymptote in this case. But then for horizontal asymptotes, we're going to have to check. So we first check for limit of x approaching infinity. So if we do this, we can first take out the x from the square root. So we absolute, just remember it's always absolute value, 1 minus 1 over x squared. Then because absolute value as x goes to infinity is always positive, so that means that if we break the absolute value, like we remove it, it'll be x plus x squared of 1 minus 1 over x squared, and this equals the limit of x approaching infinity of x times 1 plus square root of 1 minus 1 over x squared. So if you plug in infinity to this, then later you realize that'll be infinity times times 2, so it'll just be infinity. So we know that as x approaches infinity, that there is no horizontal asymptote. But we also need to check for the negative infinity. So in this case, x approaches to negative infinity. Again, there's absolute value. But the difference is that if we want x to be positive as it goes to negative infinity, to do absolute value, you need to do the negative. So x minus x. Because as we want to make x goes to negative infinity, this term will be positive. And this term will be positive. So then if you simplify this, if you try plugging infinity, you'll still get a problem because you'll get like infinity minus infinity, which is not allowed. So what you can do is you realize that there's like a square root, so you multiply it by its conjugate. So you multiply it by, I don't know, first take out x, factor x, then we can take out the conjugate. Then we multiply by its conjugate, so the conjugate will be 1 plus square root of 1 minus 1 over x squared over 1 plus square root of 1 minus x squared. And this will equal to limit of x approaching negative infinity. of x times 1 minus 1 and minus plus x 1 over x squared over 1 plus square root of 1 minus 1 over x squared. And this will just lead to limit of x approaching negative infinity of 1 over x times 1 plus square root of 1 minus x squared. Because the 1 minus 1 becomes 0, and it'll be x times 1 over x squared, which is 1 over x. So I just bring the x down to the denominator. So now it's pretty clear if I put in negative infinity that if you plug in negative infinity here, that this term will go to 0 because 1 minus 1 over x squared. Sorry, 1 minus 0 basically. So it'll be 1 plus 1, and we times by minus infinity, so it'll be like 1 over infinity, so it will become 0. So we have a horizontal asymptote as as x goes to negative infinity, and the horizontal asymptote as y equals 0. Then now for slant asymptotes, there are two ways you can do this. One of the ways is just to do it by long division, but the method I prefer is to do so by doing the limits. So in this case, because we know that there is a horizontal asymptote as x goes to negative infinity, then we don't really need to check for x approaching negative infinity, but we still need to check for the x approach to infinity. So for x going to infinity. So the way to check for the slant asymptote, so slant asymptote is a asymptote which is in the form of y equals mx plus b. So what you can do is first we find m. So m will equal to the limit of x approaching infinity, and you just do the function, so fx over x. So this will basically just be a limit of x approaching infinity of x plus square root of 1 minus x squared minus 1 over x. And if you simplify this, it will just be limit of x approaching infinity of 1 plus we know that we can factor out the x again, so it would just be square root of I'll just factor it. X times 1 plus x squared of x squared minus 1 over x. And then we can factor this so the x can cancel, so we get limit of x approaching infinity of 1 plus square root of this should be 1 minus 1 over x squared. And if you plug in infinity to this, we get 1 plus 1, so we get 1 plus 1 equals 2. So that means that we know the k value is 2. So, or sorry, the m. Our gradient of the y equals mx plus b is 2. Then to find the b, all we gotta do is just do this. So we just do limit of x approaching infinity of x or fx minus basically the mx. So in this case, m is 2, so it'll be 2x. So we get a limit as x approaches infinity of minus x plus x squared 1 minus 1 over x squared, and we can factorize the x, so we get the limit of x approaching infinity of x times minus 1 plus square root of 1 minus 1 over x squared. Now we just need to, if you plug in infinity right now, you'll get no, that's not correct. It'll be 0 in the inside, so we can't do 0 times infinity. So we still need to manipulate this limit, so we multiply it by the conjugate again. So it will be x times minus 1 over minus 1 minus 1 minus. Then you can do some similar manipulation like the previous example. Let me just rewrite in the bottom. So you times it by minus 1 minus square root of 1 minus x squared over minus 1 minus 1 minus x squared. And if you simplify this, you'll get limit of x approaching infinity of x times 1 minus 1 minus plus 1 over x squared over minus 1 minus square root of 1 minus x squared. And then you'll get limit of x approaching infinity of 1 over x times minus 1 minus square root of 1 minus 1 over x squared. So you get it to be 0. So that means that our slant asymptote is in the form of y equals 2x plus 0 or y equals 2x. So now we know that as x goes to infinity, that it will get closer to 2x, and as x goes to negative infinity, it will get closer to 0. So now we have to get the critical points. So to get the critical points, all you gotta do is take the first derivative of the function. So let's find the first derivative. So the first derivative of this will be, so we know fx equals x plus square root of x squared minus 1. So the first derivative will be 1 plus, let's do the outer function first. So 1 over 2 times x squared minus 1 to the power of negative half. And then by chain rule, we differentiate the inside times 2x. So this becomes 1 plus, the 2 cancels out, we get x over square root of x squared minus 1. Then we equate this to 0 to get the critical point. So we get 1 plus x over square root of x squared minus 1 equals 0. So that means x over square root of x squared minus 1. No, just first multiply everything by square root of x squared minus 1. So we get square root of x squared minus 1 equals negative x. And if you try solving this, later on you'll get that there's no value for this. So there will be no critical points. So there is no value, no x, so no critical points. And then to find this, so there's no local minimum and no local maximum. Then the next part is to classify to state which interval is increasing and decreasing. And to do this, you just need to test points using the first derivative. So if you draw like a number line, so generally what I would do, like what you have to do is just do fx and then draw three lines. One for the next one is the first derivative, and the next one is for the second derivative. So what you want to do is, we know that the two places that are not defined are at, it starts being defined at -1 at 1 and at 1. So that means that there's probably going to be something at 1 and -1 here. Because we want to test between these, because we know that there's nothing defined here, not defined in the middle. So we just want to test if it's increasing or decreasing at greater than 1, and if it's increasing or decreasing less than or equal to 1. So we should test this point. But generally this method, you should always include any point that is a vertical asymptote or a critical point. So you would put these dots where there's a vertical asymptote or a critical point. Then we just need to test the first derivative of x being less than -1. So if we test the first derivative at -2, we get 1 minus 2 over root 3. And we know that this will be less than 0 because this thing is bigger than 1. So that means that here is negative, so that means that it will be decreasing here. Then if we do f prime of 2, we get 1 plus 2 over root 3. So we know that's greater than 0. So after 1, it will increase. And the same thing we do for the concavity. So for the concavity, we just need to find the second derivative. So for the second derivative, we get, so we know f prime of x equals x plus, sorry, 1 plus 1 over 2 x over square root of x squared minus 1. So then if you take the second derivative, you just need to use the quotient rule. So we know that the 1 becomes constant, so it's going to become 0. So we do quotient rule on the second term. So we get 1 times square root of x squared minus 1 minus the derivative of the bottom term. So it is 1 over 2 root x squared minus 1 times 2x. And then you divide it by the square root of x squared minus 1 squared. And eventually it will simplify to, you can just simplify this, it'll become square root of x squared minus 1 minus the 2 cancels out, so it'll be x squared over 2, sorry, x squared minus 1 over square root of x squared minus 1 squared. Then you don't actually really have to simplify it so much, but what you gotta do is just put in points now, because we want to put a point that is less than minus 1 and one that's above 1 to check for the concavity in those two areas. So if it's less than 1, so we can just do like minus 10. So we know that this becomes, like if you put minus 10, you don't really need to calculate it, but you can know that yeah, we can just put in. So this will be square root of 99 minus 100 over square root of 99 again, divided by square root of 99 squared. So it doesn't matter the value, but what matters is the sign. So in this case, we know that if you multiply the top and bottom by square root of 99, then it'll become like this. So yeah. I'll just make it clear by doing blue. So we multiply the top by square root of 99 and the bottom square root by 99. So the top, this term, it will become 100 square root of 99 over 99. And we know that 100 over 99 is greater than 1. So that means that if I subtract square root of 99 minus this term, it will be negative. So it will be less than 0. Then if you do 10, so we do this, we do it again for greater than 1, so we can pick 10. So if we do 10, then we do square root of 99 again, minus 100 over square root of 99 over square root of 99 squared. So again, this will be less than 0. The same case with y. It's the same reason for why minus 10, like when I put minus 10, it's less than 0. So now we know the concavity will be going down and going down here. So if you want to find point of inflection, you just equate the second derivative to 0. So if I put the second derivative to 0, second derivative is square root of x squared minus 1 minus x squared over square root of x squared minus 1 over x squared minus 1, I think. We equate to 0, and if you multiply both sides by x squared minus 1, we get square root of x squared minus 1 minus x over square root of x squared minus 1. Then if you multiply everything by x squared of x squared minus 1, you get x squared minus 1 minus x equals 0. And if you try solving this, there will be no answer. So there will be no points of inflection. I think you can just solve it using the determinant. So if you do determinant, it'll be minus b, it'll be squared minus 4ac. So it'll be 1 minus 4 times. No, this should have. Maybe I messed up somewhere in the derivative or something, but before I did, there was no solution. So if nobody can spot my error, but I think if you try doing it again, there would be no solution for this one. And once you know that there is no points of inflection, then you can draw because we have already got all the points. So we just need to fill in the intervals because they're asking for the intervals. So if you want increasing, just find the spot here. So it will be, if you want to add an interval, then x element of so you could think of it as is this, but I saw the answer here and it also says that it should be x element of 1 to infinity. And the reason is because if you're doing derivative, we know that the x is not defined in to the left of 1. So that means that at the point of 1, there is no derivative. Because by definition of derivative, there should be like a left limit and a right limit. And if there's no left limit, that means that it is not differentiable at the point 1. So it says that you would get the mark if you wrote this, but the correct answer is exact. If you want it to be like correct, then it'll be the open interval from 1 to infinity. And the same case goes for the decreasing intervals. Oh, sorry, this is increasing. The decreasing intervals should be x element of infinity to 1 minus 1. This is the correct one. And the same reason like before, where we don't include minus 1 because there's no right derivative at minus 1. Like no right limit. Then for concavity, so we see that both of them don't have any concave up. So that means that there is none here. So this is none. Then the interval for it to be concave down is a 2 interval, so x element of minus infinity to minus 1, union of 1 to infinity. So again, just note that the point of these points, that they're not differentiable at this point. That's why we don't include it in the interval. But they say that it's okay if we include it. Then once you already have this and there's no points of inflection, none. Then once you already have all the information, you can graph it. So if you want to graph it, what I suggest is to find the y-intercept and x-intercept. But we know that in this case that it's not defined between -1 and 1, so there's no y-intercept. And for the x-intercept, we just check if the value goes to 0, like fx equals 0. And you notice that this won't happen. So then you just need to have some starting points. So what I need a starting point is for f of 1, where to draw it. F of 1 will be 1 plus square root of 1 squared minus 1, so it'll be 1. And f of minus 1 will be minus 1 plus minus 1 squared minus 1, so that equals minus 1. So we know that at f of 1 we get 1, and f of minus 1 we get minus 1. And now what you draw is just the asymptotes. So we know that at y equals 0 here we have an asymptote, the horizontal one, and we also have a y equals 2x. So something like this. So y equals 2x. I should probably do dashed lines. And then now you just draw. So we know that it's not defined to the left of 1, so what we have to just draw is to the right. And we know that as it goes to infinity, that it should approach the slant asymptote. So you should draw like that. And note that we don't draw it like this, and that we don't go underneath because it's concave down. So you think of it as like that, something like it's curving down. And the same case goes for the left. So we know that as it goes to negative infinity, it should go closer to 0. So we just draw it like that. And we know that it's also concave down. Just make sure that you pay attention to the concavity, because if it's concave up, you'd have to draw it like that, something like that. So that's how you like graph the question. So just remember the steps, how to do each part. And generally, if you're very careful with this type of question, you should get the mark, because it's just a step-by-step question that you just have to memorize to find the domain, asymptotes, then get the critical points and stating which part are increasing and decreasing. And when you want to draw the graph, if it's a little bit harder, this case was pretty easy, but some other cases it might be a little bit harder. So just write all the information you have, and then just try to picture the puzzle. So like put the asymptotes, and then just put all the critical points, and just see how the graph increases and decreases and the concavity, and you can get the graph. Yeah, so that's the last question. So if you guys have any questions, you can ask, or I think that'll be the last question.
Yeah, so if you guys don't have any questions, then like that's the end of this review seminar. And yeah, thank you for coming.
Okay, so thank you all for attending, and we'll post the recording on the AMACSS Discord server. And good luck with your final.